Assalamualaikum. For this video, we will discuss regarding the Gauss law, which is from chapter 4-4 in Fundamental Applied Electromagnetics by Ulabi. Okay, so the keywords here will be as seen here, electric flux and electric flux density, the Gauss law itself, and then the application of it. And we have integral form of the Gauss law and also the differential form of the Gauss law. Okay. So let's just recap back on the Coulomb's law, which we already go through in the previous class. So this is the equation to find the electric field using the Gauss law. So here the electric field is proportional to the number of charge and inversely proportional to the constant for 4 pi epsilon 0 and the square of the distance between the charge, which is the source for the electric field, and also the point of interest where you want to find the electric field, and the direction will be from the charge to the point of interest as notated by the unit vector over here. And as you can see over here, this will be the magnitude of the electric field. Okay, before we go further on the Gauss law, first let's revisit back on the flux of a vector. So in this case, the vector is electric field, so electric flux. So electric flux, as per the definition, is the rate of flow of electric field through a given surface or through a given area. Okay, so here you will be needing the vector itself, which is the electric field, and a surface. Okay, so the field is seen as a flow similar to the water. So here this will measure the number of the electric field that is passing through that given area and denoted as this symbol over here with this unit. Okay, so it is mathematically defined as the dot product between the vector itself and that particular surface where the electric field is going through. Okay, so dot product between E and also between surface. Okay, so which also can be translated into the magnitude of electric field, the surface area, and also the angle theta between the electric field and also normal to the surface. Okay, so for in any cases that the field is not constant, the field is not constant across the surface, which is most of the cases. So we have to break the whole surface into smaller grids. Okay, which each grid is representing a tiny surface area, or known as ds, differential surface area. And to find the flux, the electric flux that is going through only that through that surface, only that small surface, we use the differential surface area instead. Okay, so others is the same. So here we only have the flux that is going through that particular surface only. And to find the total of the electric flux through all the surface, okay, the sum of it, we have to do the integral, the surface integral, as you can see in this equation over here. The number of vector flux that is going through a surface is given by the dot product, as you can see over here, and the angle between that, which is expressed by the cos theta over here, will be affecting the total number of electric flux. Okay, so here I have an example, a few different examples of different condition of the electric field with the same surface configuration. So the first one here, I have the surface in this xy plane over here, and this will be our surface ds, and then the vector for this is given by is completed by the normal direction or 90 degrees from the surface itself. Okay, so this will give us the direction of the vector ds. And for the electric field is in the z direction. Okay, so here E is in z direction, ds is also in z direction, 90 degrees or normal to the surface itself is z direction. So the angle between those two will be 0. So completing this equation over here, cos theta is equal to cos 0, which is equivalent to 1. So here you will have the maximum number of the electric flux, okay, which is given by the magnitude of electric field and also the surface area, the total surface area for this differential surface area. Okay, so next one, we have the same surface on the xy plane. Okay, but this time the electric field is in this direction. So here we can say that the electric field is we have x component and also the y component. Okay, so now we'll see the angle between the electric field and this 90 degrees to this surface is approximately 45 degrees. Okay, so cos 45 is we have 0.7 something. Okay, so the dot product for these two vector will be less than what we have over here. And how about this one? We have again the same surface with the normal direction in z direction, and but this time we have the electric field in y direction. So the angle between E, electric field, and ds will be 90 degrees. So cos 90 is equal to 0. So here we won't have any vector E that is passing through that surface ds, which you can see over here. It is going across the surface from one end to the other end. It does not cross through the surface, unlike what we can see over here. So this here we have the maximum dot product or the maximum electric flux going through the surface. So for this one it will be in between, where only part of the electric flux is going through that particular surface. Okay, so we'll use this concept in the case of Gauss law. The Gauss law.